La, la, la. I can't tell if it's hearing anything, though. Like there's a tiny green dot.
Go to settings.
What settings?
On your computer.
I'm not doing it through the computer.
You mean you're...
Oh, wait. Somebody's here. Can you hear anything? Yes. Thank you. Oh, boy. I don't know why. It just went dead for no reason.
Probably auto change the setting.
Yeah, I don't know what happened. Okay. So everyone can hear me. Who did I just send the link to? I just sent the link to 303. I'm going to send it to 212. Hopefully everything's working. Hi. Okay, I have 2 people here. And everyone can hear me, so that's a good thing. Okay. We're going to give it like 2 to 3 minutes to let people filter back in. Okay, we got another. Good. Hi, welcome. Welcome. Ooh. Hi, everyone can hear me, right? We're good? Can you go over polarity until they come? Bond polarity, molecule polarity, or both? Any chance you can get me a fork?
Throw one down.
Hmm?
I'll throw one down.
Thanks. The bread is so bad. Okay.
I bet you it's on the keto.
No. Not until after my Super Bowl. Okay. Waiting for people to come back in. We have polarity. No, that was not Billy.
Here's a fork.
Okay, hold up. Ah, what the heck? Oh, and okay. Hold up. I still need a minute. No, you guys can talk to Billy in a little bit. Okay, Poopy, come on. You can't stay down here. You're too needy. Come on. That's a good boy. Find your dad. Okay. All right, so polarity. Just pausing, waiting for everybody to come in. There's 2 types of polarity. We have bond polarity and we have molecule polarity. That's not writing. Okay. We have, for bond polarity, that is asking us, ooh, now it's all freaking fuzzy. What the heck? Okay. Okay, bond polarity. Let's say we are looking at a molecule of chloromethane. For chloromethane, this bond is a polar bond. How do I know that? Because if I look at table S for bond, backing up, bond polarity, you're going to use the acronym BEND. Bond electronegativity difference. Literally subtract the electronegativities. Look them up on table S. Carbon is 2.6. Chlorine is 3.2. Subtract them. It's greater than 1. That's considered a polar bond. Then to look at an entire molecule, we use SNAP. You split the molecule like this in a plus sign. If the top is the same as the bottom and the left is the same as the right, your molecule is symmetrical and nonpolar. If you have something different, the top is different from the bottom, or the left is different from the right, or both is true, then your molecule is asymmetrical and therefore it's polar. Super simple. Okay. What question were we on? 38? I think we were on 38. Let's get back to the test. Okay, 38. We have 4 aluminum, 3 oxygen, and 2 aluminum oxides. Yes? Okay, so to do this, we have how many moles of aluminum react completely? Let's say I'm moving from 3 moles of oxygen. Now I want to use 4.5. And instead of getting 2 moles of aluminum oxide, I want to get 3. That's 4.5. This is a ratio. If they worded this a little bit differently, this very well could have been an Algebra 1 question. So how this works. Every time I set up a ratio, since the time I was in 7th grade, this is how I did it. When I have 4 moles of aluminum, I need 3 moles of oxygen. Maybe write yourself a little note here, right? I need to know how many moles of aluminum I would get if I used 4.5 moles of oxygen. Cross multiply, solve for X. 4 times 4.5 is what? 20? 22? I don't know. I'm a chemist, not a mathematician. Sorry, just pulling up the calculator because I'm not prepared. I'm also a little bit crazy. 4.5 times 4. We're getting 18. 18 is equal to 3x divided by 3. X is giving us 6 moles of aluminum would be needed. That is going to be choice 3. Now, Jared inserted an excellent point. Common sense says it's 3. Now, what he means by that. If we are increasing the amount of oxygen and we're increasing the amount of aluminum oxide, we logically have to be increasing the amount of aluminum we use. The only choice that's going to increase the amount of aluminum is choice 3. Based on where this falls in the test, you didn't have to do any math. It was really just common sense. But if you did the math, this is what you would have gotten. Nice job, Jared. Killing it. So smart. Yes, so smart. Just FYI, I'm eating pasta. Okay. 39. What is the percent composition by mass of oxygen in calcium nitrate if the gram formula mass is 164 grams per mole? Okay, this is awesome because they give me the equation. The equation's on table T, and they already gave me half of the problem. 4% composition. Oh my goodness, this dog. Percent composition by mass is here. It's the mass of the part divided by the mass of the whole times 100. So the part is the thing that we're asking about. That's going to be oxygen. Table T, back cover. You cannot eat my pasta. No. This mass of the part over whole. Part is going to be oxygen. And the whole is going to be the entirety of the calcium nitrate. They told us in the question that the calcium nitrate was 164. not 2, 4. 164. So the question is, how much oxygen do I have in calcium nitrate? Distribute, just like in math. Outside the parentheses, this 2 goes in. 2 times 3 gives me, it gives me 6 oxygens. That's not O. That's not 0. That's an O. I have 6 oxygens. If I look at the periodic table, 1 oxygen has a mass of, it's 16, but I'm just going to show you. Oxygen has a mass of 16. You don't have to do 15.9994. Not that important. So I have 1 oxygen. Its mass is 16. No, I have 6 of them. 6 times 16. How come we're doing 2015? Because we did 16 and 17 during Saturday school. 6 times 16 gives us 96. Oxygen, out of this 164 grams, oxygen is worth 96 of it. So what I'm going to do is the 96 divided by 164. Sorry, this is really bright. 96 and 164. There's my answer. I'm going to multiply that by, oh, dear, what did I just do? 96 and 164 times 100 gives me 58.5%. I'm looking at the wrong thing here. 58.5% is rounded to 59. Choice 4. Nice job, people. Nice job. So when we did this in class, I made you figure out this 164. You did that by adding up all the parts. You have 1 calcium. This 2 distributes to the nitrogen. You have 2 nitrogens and 6 oxygens. So you would have added them all up. We did it like this. Calcium, nitrogen, oxygen. We did the number of atoms. You had 1 calcium, 2 nitrogen, 6 oxygens. You would take the mass from the periodic table. Calcium's 40. Nitrogen is 14. Oxygen 16. You would have multiplied those. That's 40, 28, 96. Then you would have added them, and that would have given you the 164. That's how I would have made you do it. But they gave you the 164 to put on the bottom. Alrighty. Moving on to number 40. Oh, we're done with this page. And all of these pages I've already drawn on. Holy smokes. We are flying through the paper here. Okie doke. 40. Here we have a balanced equation. Which type of chemical reaction is represented by the equation that I'm not showing you? Which type of chemical reaction is represented by this equation? So we have lithium and nitrogen. They're coming together and they're forming a compound. That is definitely going to be synthesis because you are forming something. Yep, nice job, Jared. The decomposition would have been breaking this apart. It would have been the reverse of this. Decompose, break down. Single replacement is what I like to call the dirty homewrecker reaction. That is where you have maybe something, I don't know. We'll just do the sample. AB plus C is going to give us CB plus A. So what happens, C is our little dirty homewrecker. C is this nice, beautiful compound, comes in, breaks them up, kicks A out. That's a single replacement. The double replacement is going to be the full swap, where we have A, B, C, D. The thing that we use to remember it is that A always wants the D. So A and D are going to pair up, and we get CB because we list positive, negative. That guy's positive. That guy's negative. Positive, negative. It's the only way to swap them. And I think that was all the options. Okay. 41 is a hidden vocabulary question. For 41, a molecular compound means we're forming something covalent. So which of these is going to give me something covalent? Okay, out of all of these, choice 2 is the only one that's going to give me something covalent. Remember, when something is covalent, it means that we have 2 nonmetals and they are going to be sharing their electrons. So out of all of those, hydrogen and sulfur are the only 2 pairs that are going to be covalent. The equivalent term for something ionic, so we generally say that they're compounds, right? When 2 things bond in fixed proportion, we call them compounds. The covalent one is going to be called molecular, and the ionic one is going to be called salt. The reason we call them salt is because they are crystals. They're not always like white crystals, like table salt, but they are going to be crystals. They do come in like basically all the colors, but that's just what we call it. So when a chemist says salt, it doesn't mean table salt. (42) Compared to a 1 mole sample of NaCl solid, a 1 mole sample of NaCl liquid has different what? Number of ions, empirical formula, gram formula, mass, electrical conductivity. I certainly dislike this question. Gram formula mass is definitely out because that's a mass of 1 mole, and we have 1 mole of each of them, so their masses are going to wind up being the same. Empirical formula, they both have the same empirical formula. Number of ions is like a mole question. They have the same number of ions, which leaves us with choice 4. Now, this goes back to earlier when we were talking about electrolytes and their electrical conductivity. The reason they are conducting electricity is because they have mobile ions. NaCl has ions, but they're locked in place in that salt or the crystal lattice. And then we have the NaCl liquid where these ions are able to swim around. When they're able to swim around, they can conduct electricity. Because ionic stuff has super, super, super high melting points, we don't even usually call this the liquid phase. We say that it's molten because that's how freaking hot it is. It's almost like lava, like it's that hot. Okay, 43. Which property of an unsaturated solution of sodium chloride in water remains the same when more water is added to the solution? Which is going to remain the same. This is not even really a chemistry question. I would say this is a logic question. Density of the solution is going to change. Boiling point is going to change. The percent by mass of water changes because you're adding more water. The amount of sodium chloride in the solution is going to stay the same. No matter how much water you add, the sodium chloride is still there. If you drink it and you add more and more and more and more and more water, you're going to not realize that it's there, but it's still there. Okay. 44. Which ion combines with barium to form a compound that is most soluble in water? Which combines with barium plus 2 to form a compound that's most soluble in water? Solubility should send you directly to table F. Okay. On table F, we are looking for something that is soluble. Oh, this is kind of a pain in the neck. We have to look up all of these. Okay. S minus 2 is this first answer choice. S minus 2. That is sulfide. They tell you that it's S minus 2. In this one, it is going to be insoluble unless it's combined with group 1 or ammonium. Barium is neither of those, which means it is going to be in the circle that you would draw here, which makes this insoluble, not the answer. Hydroxides are here. They are insoluble unless they're combined with group 1, calcium, barium, strontium, or ammonium. Barium is here. We're looking for something that is going to be soluble. When I mix barium with hydroxide, I'm going to get something that falls outside of this inner circle, which makes it soluble. So it is choice 2. Nice job, guys. Question 45. We're looking at a sample of gas in a sealed, rigid container. So that would be something like my coffee cup that I drink out of every single day. Is going to be something metal, like this right here, actually. This would be a rigid container. You can't squeeze it. Like a regular disposable water bottle is squishy and you can like sort of change its shape. Rigid container means its shape is not changing. When we have a rigid container, that means our volume is going to be constant. Okay, so we have a sample of gas cooled, temperature is dropping. In a sealed rigid container, the pressure is going to decrease, but the question is why? Remember, pressure is a force of pushing. So if our pressure is dropping, temperature is dropping. When temperature drops, it means that these molecules are flying around slower, right? We don't actually draw particle diagrams like this, but we can imagine they're slowing down. They may have started doing something like this, where they were flying around like crazy. Temperature drops, they move slower. So if they're moving slower, they're going to bang into the walls less often. And they're going to hit with less force. Think of like driving a car. If you are driving at 12 miles an hour and you hit somebody, it's not going to hurt. If you're driving 80 miles an hour and you hit somebody, they're going to like get really crazy hurt. They're going to break bones. Less often, less force. That's the reason. So that would be choice 1. Ooh, Carlos, I see you're here. You can actually backtrack because we did part A and we kind of got shut off. The YouTube should have saved it. I hope it's there. I don't really know. But if you want to go back to part A, you're more than welcome to. If you want to hang out and backtrack later, that's fine too. Okay, I'm still here. I'm sorry. I'm eating. Oh, thank you guys. I didn't know it saved. Okay, 46, another gas loss question. This one, we have a rigid cylinder with a movable piston. So that's kind of the opposite. We have a rigid cylinder. Kind of think of it like a syringe, basically. What happens is we're going to have like this rubber piece in here. And we have like a plunger where, like, if this were like a vaccine or a shot or something, the nurse would put their thumb here, squeeze, and then this is going to shrink. So your volume could actually shrink, but it could also go up. Your volume can change. So if your volume is changing, we have a movable piston. This is going to hold 50 liters. We're at 30 degrees Celsius. What is the new volume of the gas? Blah, blah, blah. This stinks. So what's going to happen is we are going to have to set up gas levels. We have 50 liters for the volume. We have 30 Celsius for the temperature. And the pressure is going to be 1 atmosphere. What is the volume of the gas if we change it to STP? That's the question. What is STP? So if we look at table A, that tells us what STP is. So we have standard pressure, 1 atmosphere. That's what we already had. Nothing changed there. And our standard temperature in Celsius is going to be 0. The important thing is that you maintain the same units. So this temperature is going to drop to 0. Now, we cannot do this problem the way that it exists right now because this is asking us to fill in to the combined gas law that you can find on table T. The combined gas law is right here. PV over T equals PV over T. So what happens? PV over T, we did before and after. Other people do 1 and 2. That's what the reference table says. I like before and after better because it's simpler and there's less little thingamajiggies. So having this temperature equal to 0 up here means that in our after, we're going to have to divide by 0, which is definitely not allowed. So we have to take these two values and convert them to Kelvin. So what happens, this temperature gets changed to 273 Kelvin. That is what's listed on table A. They're both listed as standard temperature, telling you their equivalent values. So you would have to take your 30 degrees Celsius and convert that to Kelvin. You can do that with this equation down here on the back cover. So you would take your Celsius degrees, add that to 273. You would wind up getting 303. 8, 9, 10. Yeah. 303 Kelvin. So you plug that in. Pressure is constant. So it's the same on both sides. You don't have to include it. Your volume is 50 liters over your 303 Kelvin. That is equal to an unknown volume. Leave it V, why not? And that's 273 Kelvin. You would cross multiply. And then you would divide. I'm not a mental math genius, so I'm going to do it on the calculator. 273 times 50 is giving me 1,650. I'm going to do this. and that. So I get 13,650 equals 303 times an unknown volume, divide by 303. And here I would wind up getting 45 point, not 1, 45.0 liters actually. So that is going to leave me with choice 2. Another way to look at this is that given all of my variables, the temperature is dropping. If the temperature is dropping, but my pressure is staying the same, my volume should drop because it's V over T equals V over T. If my volume is dropping, my temperature should also drop. So you could eliminate these two choices because they're bigger than the original. And then these are smaller. It's just a matter of how much smaller it's going to get. Okay. Next is 47. Sorry, I folded it funny. Given the potential energy diagram for the chemical reaction, given here, which numbered interval represents the heat of reaction? So heat of reaction has a lot of names. We call it heat of reaction. We call it enthalpy. We also call it delta H. For those of you who remember, delta H is equal to products minus reactants. And on a potential energy diagram, your reactants come first, your products come after. If you were to subtract your products, let's do this. Let's color code it. Your products are going to be green. This arrow represents your products. Your reactants are going to be this weird yellow color. Those are your reactants. If you took a ruler and measured 3 and 1 and then subtracted them, you would wind up getting, for your delta H or your heat of reaction, you would get arrow 4. Arrow 2 is your activation energy. That would be how much energy you needed to get from your reactants to the tippy top of your reaction. That's literally where your reaction is taking place. And then this is all of your energy being released, but you absorbed more. So this is an endothermic reaction because the net energy change is positive. You would wind up getting a positive delta H if these actually had numbers. But this one's higher, this one's lower. Say it's 50 and 40. Subtract them, 50 minus 40, you get a positive 10. So your delta H is positive. It's endothermic. Low to high, more energy has to go in, then comes out. There's a lot of ways that we know this is endothermic. Okay. Oh, and I scribbled all over it. I'm sorry, this is kind of difficult to see. But you should have a copy in front of you. Okay. Base your answers to 48 and 49 on the graph below and your knowledge of chemistry. This is good stuff. Okay. What is represented by the number 1 in the IUPAC name for these alcohols? We have methanol, ethanol, and these are the ones they're talking about. 1 propanol, 1 butanol, 1 pentanol. So we know that when they put numbers in front of organic names, that is telling us where the functional group is. So in this case, our functional group is the OH. That makes this an alcohol. And that tells us where it is on the molecule. So that is going to be choice 3, right? Number of OH group for each carbon atom. What is number 2 asking? The number of OH group. Oh, the number of OH groups. That's not okay. 3. It's answer choice 3 for those of you who were wondering. The location of an OH group on one end of a carbon chain. Realistically, an alcohol could go on the end or in the middle, but because these are all ones, it's telling you it's on the end. Does that help? Because the aldehyde and the ketone are location specific. alcohols can go anywhere, but because it's number 1, it's telling you it's on the end. Okay, so 49, what can be concluded from this graph? We are seeing that we're changing alcohols here, temperatures rising. These are the boiling points of the alcohols. So really the question is, what is the difference between all of these alcohols? If you looked at table P, I don't remember which one. P for prefixes. If you look at table P, methanol would have 1 carbon, ethanol would have 2, propanol has 3, bute, pent. We're increasing the number of carbons as we're going across this x-axis. So this is data reading. This is and a little bit of reference tables. The greater number of carbon atoms per alcohol molecule, the higher the boiling point of the alcohol. That's what this graph is telling us. Just choice 4. That's it. Okay, moving on. Question 50, last multiple choice. Here we have more data. In the lab, a student investigates the effect of concentration on the reaction between HCl and magnesium solid, changing only the concentration of HCl. Data for 2 trials are shown in the table below. Compared to trial 1, what is the expected reaction time for trial 2, and explain the result? Okay, we got to read this table. Trial 1, we used 50 milliliters of HCl, and it was a 0.2 molar concentration. So that means we had 0.2 moles for every liter of HCl or water. And then the mass of the magnesium was 0.1 grams, and the reaction time was 48. Then we're still using 50 milliliters, but concentration is going up. So concentration realistically is defined by how much solute you have dissolved in your solvent, blah, blah, blah. I describe it as how much stuff is in your other stuff. So this is how much HCl is in your water. That's what this literally means. So we have 0.2 HCl in the water. This is 0.4 HCl in the water. So we're increasing the amount of HCl. How this happens, we are increasing the concentration of HCl. Our reaction time realistically should go up. I'm sorry, down. It should go down. So as it's going down, the question is, why is it going down? Reaction time is going to go down because of collision theory. Right, as we're adding more HCl particles, they're going to collide with these magnesium particles more often. So if they're colliding more often, this reaction is going to happen faster, and the amount of time it takes is going to drop. So it's going to be less than 48 seconds because there's more effective collisions per second. So yeah, it's going to be choice 2, reducing the amount of time it takes them to collide. Perfect. That right there is our last multiple choice question. You do not need any specific number, like which particular questions you need. You just need any 50 to pass. So the first 30 should be pretty easy. And then you just have to find 20 to 25 more throughout the rest of the test. The questions do get more complex as you go, but I really don't think they're any more difficult. Okay, so right here, we are going to take just a 2-minute break. Because we've been doing this for 2 hours now. Two minutes. After this stream, you definitely should just go like watch Netflix. Go wash your brain. You need to like let your brain relax. Go to sleep. Take a nice hot shower or a cold shower, you know, whatever is better for you. Relax your brain. Are we in the same room for the test? I think we have 3 rooms. Definitely play video games. Like, maybe some people will, some teachers will tell you to like read before the test. No, don't do that. Like I'm telling you, go cool off. Go be a kid. Relax your brain. Whatever you know, you know. The test is starting at 9 o'clock. You really should be there like 8:30-ish. I am actually going to be there. There was like a schedule mix-up. I am going to be there. I'm going to be sitting in the hall. Don't eat breakfast over the test. Eat breakfast before you get there. Okay, are we ready?
No, you can't have any pasta. No. No. You're cute, but no. Pasta is not good for a baby.
Okay. B2s. Kind of the same as B1, except they're a short answer. So, determine the volume of 2 molar HCl solution required to completely neutralize 20 milliliters of 1 molar NaOH solution. 48 and 49. Backtracking super quick. 48 and 49. The one in front of these names is telling us where. What? Sure. He's eating your food. The dog just jumped and is eating the food. I'm sorry. 48. The one means the location of the OH group. And the one specifically is telling you it's on the end of the carbon chain. And then from here, yes, it is 3 and 4. The 4, the greater number of carbon atoms per alcohol molecule, the higher the boiling point. 1 carbon, 2 carbon, 3 carbons, 4 carbons, 5 carbons. Prefix comes from table P. Okay. 51. 51 is the titration equation, which is on table T. Seriously, you don't have to memorize like anything for this test except the vocabulary words and the average atomic mass equation. 51, titration. Mass times volume of the acid is equal to the, I'm sorry, not mass, the molarity. The molarity and the volume of the acid is equal to the molarity and the volume of the base. So just pair it up correctly and do the math. So we have very little paper left. 2 molar, sorry, you can't see. 2 molar HCl. I am trying to figure out the volume. The volume is a question. How do you know it's titration? By definition. They're asking you to neutralize. You know that this is an acid, this is a base. It's just knowing the process of titration. So we have 2 molar acid. We don't know the volume. We do know that we are looking at 1 molar NaOH, and we're looking at 20 milliliters of that. So we're going to do MVA equals MVB. We have 2 times an unknown volume is equal to 1 times a volume of 20. 20 equals 2V divided by 2. V equals 10 milliliters. I would need 10 milliliters of the acid to neutralize 20 milliliters of the base. The reason is because this is twice as much HCl as we have here. It's crazy how you guessed 10. It's a good guess. What happens, you're going to get a white book that has all the questions. It's going to be like this. Comes in like a 16-page book. Then we have, you're going to get a reference table. You're going to get a bubble sheet. And then you are going to get like a yellowish colored book that you write all of these answers in. So what they're going to do for this question in the answer book, it's going to have 51 blank ml. You almost never have to put the units. Like almost never. Yes, the 20 equals the 20, so it's neutralized. Realistically, a better way to look at it is that you would have, I mean, it does multiply that it's 20 and 20. Yes, that works. So that's good. Moving on. 52. Determine the mass of KNO3 that dissolves in 100 grams of water at 40 degrees Celsius to produce a saturated solution. What table are we looking at? You tell me. G. Yep, table G. Table G, everybody's favorite mess. Okay. Table G. I hate this table. I will be the first to tell you that this is dumb. Okay, table G, how does it work? We have solubility, which is how well something dissolves when it's in 100 grams of water based on the temperature. The lines that go up are things that are solid. We know that solids dissolve better when the water is hot. Then as water is getting hotter, gases are more able to escape because those water molecules, they're moving faster. The water molecules are trying to spread apart. As they spread apart, the gas can come up and escape between them. So that's why gases are less soluble as the temperature is climbing. So we specifically were asked to look at KNO3, which is this really steep line here. It's going up. So we know that KNO3 has to be a solid. And then we need to know if we're at 40 degrees Celsius, how many grams of KNO3 will give us a saturated solution. So saturated means it can't hold any more. It is the point that touches the line, and that comes out somewhere between 60 and 70. I would maybe guess like 64. 64 grams of KNO3 in 100 grams of water. That is when stuff is just going to start to accumulate on the bottom. Anything over the line, remember, is going to be saturated. It could be supersaturated, but they have to tell you in some way that this above the line point is going to be homogeneous. And then underneath the line means that we are going to have an unsaturated solution, which means the water could hold more stuff. It could dissolve more stuff. So the way it works on the test, you would say 63, I would say 64. If somebody says 68 or 69, then they're wrong. If somebody says 61 or 62, then they're wrong. They give you like a range on the test. They would say like, if your answer is between 63 and 65, it's correct. They give a range. So that is that. Then we have question 53. State in terms of molecular polarity why ethanol is soluble in water. Any ideas on that one? Why is ethanol soluble in water? This goes back to the aquasand lab that we did. We did oil and water, well, vegetable oil and water, baby oil and water, mineral oil and water. Because it's not good enough, when the question says state in terms of molecular polarity, halfway there, that means that the word, ooh, way to go, Jared. It's polar, and polar dissolves. Here we go. We know water is polar because water looks like this. You always draw it at a right angle, right? Somebody asked me earlier to describe polarity. This is where it comes in. You always draw water as a right angle because this gives you the correct answer. Left and right, they are not the same. Top and bottom are not the same. That is asymmetrical. That makes it polar in the acronym SNAP. Symmetrical, nonpolar, asymmetrical, polar. This is not symmetrical. When you put A in front of a word, it means the opposite. So this is asymmetrical and polar. I'm going to do the same thing for ethanol. F is 2 carbons. All would be OH. Let me just put a line here to separate. OH. There's all my H's. if I separate this molecule, top and the bottom are not the same. This side has an OH, this side does not. If I split it in the middle, right side has an OH, left side does not. So this would also be asymmetrical and polar. We determined in that lab that polar stuff mixes with other polar stuff and non-polar stuff mixes with other non-polar stuff. They have like a little rhyme or phrase for it. They say like dissolves like. Now, that sounds kind of stupid. Like dissolves like. What it really means is that when two things are the same polarity, that's when they will mix. Polar dissolves in polar. Non-polar dissolves in non-polar. That's it. So for this answer, you would say, because ethanol and water are both polar, they will dissolve. And that satisfies talking about molecular polarity. You have to use these words if they say state in terms of. Because ethanol and water are both polar molecules, they will dissolve. Good? Okay. 54 through 56. 3 elements, D, E, and Q. They had to pick capital letters that didn't already exist on the periodic table because they wanted to do D, E, and F, but F is fluorine, so they had to just pick another letter. Okay, so these elements are in period 3. Some properties of them are listed below. A student's experimental results indicates that the density of element Q was 2.10 grams per centimeter cubed at room temperature and standard pressure. Identify the physical property in the table that could be used to differentiate the samples of the 3 elements from each other. Okay, so physical properties, things that you can see, smell, taste. You shouldn't be tasting your experiments, but in some cases you can. The density would be a physical property. Hi. Okay, so the only thing that's actually different here is their densities. That would be the physical property we can use to differentiate these samples. Sometimes you can use phase to differentiate. It's definitely not the best answer because most elements exist in all phases. Yes, hi, Addie. I miss you too. So, density is on, yes, table S. Density is on table S. They can only put it on table S because it is different for all of the elements. All the elements have their own density. So we can use density to differentiate these samples from each other. So nowhere on the test does it tell you you have to write in complete sentences. You can just write the word density and that's it. Okay. Next, we can identify the group on the periodic table to which element D belongs. So it's kind of multiple choice because there's only 18 groups on the periodic table. So your answer choice has to be 1 through 18. So we know it's a solid. Its density is less than water, so it'll float in water. And this is probably the most important part, is that its formula would be D2O. Okay. Let's see if we can figure this out. D2O. Where does it go on the periodic table? Best way to figure this out is to figure out what the charge would be on this element. If I can figure out the charge, then I can typically figure out where it belongs. So this 2 that's down here came from the oxygen with its -2. This has to be something positive. If we look, there is an imaginary 1 down here. So this would have put this guy in group 1. Now, hydrogen would be a decent guess, but hydrogen is in the gas phase. And this question says that element D is in the solid phase. So I probably would have guessed lithium would have been my guess, but it doesn't even ask you what element it is. It just asks you what group it would be in. So because it's a +1, every member of group 1 has a +1 charge. Every single member of group 1 has a +1 charge because they all have 1 valence electron. So that's how you would figure that one out. Next is 56. Determine the percent error between the student's experimental density and the accepted density of element Q. Sorry, I didn't realize you couldn't see that. So we have to do some math here, which takes us to table T. Anytime you got to do math, you go to the back cover. Percent error is right here. We have the measured value minus the accepted value over the accepted value times 100, blah, blah, blah. Like 3rd day of school, I taught you this. And this is how it goes. When I was in college, this is how I remembered it because there were no reference tables in college. Percent error equation is used to tell you how wrong you are or how precise your experiment is. So if you're like, your density is supposed to come out 2, but you're getting 5, that means your precision is terrible. It means your accuracy is terrible. If you're getting 210 and you're supposed to get 2, your accuracy and precision shouldn't be that terrible. That's why we use the percent error equation. I'm sorry, I have the hiccups. So to do this, we do Bob minus science over science because I name everybody Bob. Another way to remember this is that you are trying to figure out how bad you did at science. That's not English, but you're trying to figure out how terrible you were doing in science, how much BSing you did. So you are Bob. According